So today we're going to be discussing neutralization reactions. And by the end of this presentation, you should understand how to calculate what's known as the equivalence point of a reaction. So first off, what is a neutralization reaction? A neutralization reaction is a reaction in which an acid and a base react as reactants to form water and salt as products. The part that's really reacting is the hydrogen ion from the acid and the hydroxide ion from the base. When those two parts react, they come together to form H2O. The other ions that are present in the reactants come together to form an ionic compound known as salt. Since water has a pH of 7 and water is neutral, that's how these reactions get their name. We're taking a low pH acid and a high pH base, and when we put them together, they form a product that's neutral. The concentration of hydrogen and hydroxide has to be equal in order for the solution to be neutral. And that point at which the hydrogen and hydroxide concentrations are equal is the equivalence point. We're going to work through a problem in order to understand how to solve for the equivalence point of a reaction. So in our example problem, we need to calculate the volume of 0.10 molar hydrochloric acid required to neutralize 50 milliliters of 0.12 molar magnesium hydroxide. The first step in doing any kind of chemistry is to write a balanced chemical equation for the reaction that occurs. So here is our equation. The formulas for hydrochloric acid and magnesium hydroxide were provided to us. We know that the hydrogen from the hydrochloric acid and the hydroxide from the magnesium hydroxide are going to come together and form water. The other ions that are present are magnesium and chloride. So the last product is magnesium chloride, and a subscript was needed to balance the charge between magnesium and chloride. So make sure that you write those formulas based on charge. The last step is to go through the equation and use coefficients to balance. We need coefficients of 2 in order to balance the number of hydrogens and oxygens on both sides of the equation. The next step is to look back at the problem and calculate how many millimoles of known we have. So we were given the information that we have a 50 milliliter sample of 0.12 molar magnesium hydroxide. That's our known. They were asking us a question about the hydrochloric acid. We did not know the volume of hydrochloric acid, so that substance is our unknown at this point. What was known was both the volume and molarity of the magnesium hydroxide. Usually we would use this triangle and the formula for molarity to calculate moles. However, it might be simpler to keep our volume in milliliters. So if we keep the volume in milliliters, instead of calculating moles, we're calculating millimoles. So it works exactly the same way mathematically, but the unit is different because we're using a different unit for volume. So when you use liters to calculate moles, you're using a regular calculation. When you leave the volume as milliliters, you are calculating millimoles rather than moles. And since we're dealing with milliliters, it's simpler just to keep it milliliters and then call it millimoles. So looking at the triangle, if we're trying to calculate millimoles, then we need to take the molarity we were given and multiply it by the volume in milliliters. So the molarity was 0.12 and the volume was 50 milliliters. That gives us a product of 6 millimoles of magnesium hydroxide. So that's how much magnesium hydroxide is present in the solution. We need to understand that an equal amount of hydrogen is necessary in order to reach that equivalence point. But we also have to pay attention to the equation we wrote. In the equation we wrote, there were coefficients of 2 in the equation. It takes 2 moles or 2 millimoles of hydrochloric acid to neutralize every 1 mole or millimole of magnesium hydroxide. So we need to set up dimensional analysis to figure out the exact amount of hydrochloric acid necessary to neutralize the magnesium hydroxide present in the solution. We know that we have 6 millimoles of magnesium hydroxide. If 1 millimole of magnesium hydroxide requires 2 millimoles of hydrochloric acid to form a neutral solution, then 12 millimoles of hydrochloric acid are necessary. So I took the amount of known and used the mole ratio to figure out how many millimoles of unknown were necessary to reach the equivalence point. Then we have to use that information to calculate the volume of unknown necessary. Remember, we're looking for an amount in milliliters. We know the molarity of the solution is 0.10. Again, we're going to use this triangle to figure out how to set up our calculation. If we're looking to solve for milliliters, then what we need to do is take the amount in millimoles and divide it by the molarity that was provided. So we know that we needed 12 millimoles of hydrochloric acid and that the molarity of the hydrochloric acid is 0.10 molar. If we take 12 and divide it by 0.10, that leaves us with a volume of 120 milliliters of hydrochloric acid. So that's the answer to the problem. There's actually a shortcut to doing this though. If we understand that the equivalence point is when those two things are equal to each other, and we know that we always find millimoles by using the same formula. It's always the molarity times volume. Then basically we can set the molarity times volume of the acid equal to the molarity times the volume of the base and sort of skip the thought process required. This is going to be the equation we can use as a shortcut. Notice that we have the molarity of the acid multiplied by the volume of the acid multiplied by the number of hydrogen ions that are present in the acid's formula. We set that equal to the molarity of the base times the volume of the base times the number of hydroxide ions present in the formula. We have to keep the number of hydrogen ions and hydroxide ions in this formula because we're not using the mole ratio. In the previous example, we used the mole ratio to do that conversion. But if we're going to use this shortcut equation, then we need to plug in the number of hydrogen ions that dissociate from the acid on the acid side and the number of hydroxide ions that dissociate from the base on the base side. We plug in all the numbers that we know, and you should only be missing one single variable, so then you're going to solve for that one. So using the equation for the shortcut and the information that was provided to us in that example problem, we can go ahead and solve it using the shortcut. So the molarity of the acid was given to us as 0.10. The volume was unknown, so I left that as x. The number of hydrogen ions in hydrochloric acid is 1. There's a single H in HCl. The molarity of the base was 0.12. The volume of the base provided to us was 50 milliliters. And in the formula magnesium hydroxide, there are 2 hydroxide ions because of that subscript on Mg and then parentheses OH, 2. So if we look at that algebraically, we need to go ahead and multiply both sides of the equation. So if I multiply on the acid side, I end up with 0.10 times x. And then on the base side, if I multiply all of those values, I get 12. Then to solve for x, we need to divide both sides of the equation by 0.10. And again, we end up with the exact same amount. It's 120 milliliters. So you can see that this shortcut formula actually saves a lot of time. I did want you guys to understand the process, which is why we talked about how to solve for millimoles and set millimoles of acid equal to base. But this shortcut just goes ahead and sets them equal to each other right away. So you just have to kind of plug and chug these equations. I do want to point out that although we discussed strong versus weak acids, there is no difference whenever we are calculating equivalence. It doesn't matter if the acid that we're neutralizing is strong or the acid we're neutralizing is weak. Reactions between the hydrogen ion and the hydroxide ion will occur whether those guys are dissociated and floating about freely in the water or not. So even if they remain attached to the acid molecule, they are still going to react in an acid-base reaction. So it does not matter whether you're dealing with a strong acid or a weak acid. The only thing that matters is the number of hydrogen ions that dissociate in the formula versus the number of hydroxide ions that dissociate in the formula. So it doesn't matter what percentage they dissociate by, it just matters how many of them are present so that you can plug them into that shortcut equation. I hope that now you guys understand how to calculate the equivalence point of a reaction. I also hope you understand what's happening between the acid and the base, the products that form, and what equivalence really means.